Hello, and welcome to today's webinar, The Inside Story on Thermoplastic Composites for Aerospace Product Design. I'm Amanda Hosey, your moderator for this 60-minute program, which explores modern advancements in thermoplastic composites and their benefits for the aerospace industry. Our speakers today come from Victrex. Jonathan Sirks is the company's head of business development. Peter Levesque serves as engineering manager, and Claire Stagel Murphy is the Strategic Technology Manager. Between them, they have more than 44 years of experience in the composite materials industry. If you have questions for our speakers, please send them to the Ask a Question box. We'll address as many as possible at the end of the program. Also note that a PDF of today's slides may be downloaded under the Event Resources tab. Now, on to today's presentation. Welcome, Jonathan, Claire, and Peter.
Thanks, Amanda, and thank you to the audience for attending and providing us with this opportunity to speak with you. On the agenda for today, I'll share a bit about Victrex with you. I will provide a comparison of thermoplastics versus thermosets and metallics. I will review the Victrex A250 polymer and where that kind of fits in the realm of thermoplastic materials. Claire will then discuss composite allowable databases, both the generation and the use. And then Pete will spend the bulk of our time reviewing modeling approaches for both composite parts and hybrid overmolded parts. And we'll end off or round out the hour with a lively Q&A. So Victrex is the inventor of the PEEK polymer. We're organized by end use applications or markets, and we've been on a polymer to parts journey where we're vertically integrated back through the monomer. But then also are able to produce different polymer product forms like tapes, filaments, films, and then parts like the hybrid overmolded parts that we'll spend some time discussing today, but also including pipes and gears and trauma plates or knees for implantable applications. So Victrex PEEK polymer, it sits at the top of the polymer pyramid. It's a semi-crystalline polymer. It's very high performance, and it provides a unique combination of properties. So if you look at the wheel there, you'll see things like temperature resistance or chemical resistance, electrical properties, inherent recyclability, mechanical strength, wear. Those individual properties can be found in a number of the polymers in the pyramid, but when you're looking to have all of those benefits, or a chunk of them, say maybe 3 or 5 of those benefits, then PEEK starts to look really attractive because it can do a bit of everything and do all of it well. And before we jump to the next slide, I'd like to share an audience poll just to get a sense of what everybody's background is. So if we could jump over to the survey, that would be great. Just another 15 seconds. Okay, it looks like the audience is kind of split between slightly and moderately familiar, so that's great. We'll be able to spend some time exploring the benefits in the next section, and then the generation of use of the allowables will also, I think, be helpful in kind of boosting the familiarity of the audience. So as mentioned, we'll review both the thermoplastic versus thermosets and metallics here. So I won't go through this entire laundry list, but what I will say is that the benefits of thermoplastic versus thermosets, or the differences, are really fundamental to the chemistry. So with thermoplastics, you're not looking for any cross-linking. You're really, when processing the polymer, you're melting it and then refreezing it off. So when running through the list, you keep that in mind. And then if asked to kind of guide you towards thermosets or thermoplastics, what I would generally say is that, if you're looking for inherent toughness, thermoplastics are inherently tougher than the more brittle thermosets. But on the other element that I really tend to focus in on is the production rate expectations. Because of the shorter cycle times, you get a lot more production out of single tool sets or capital equipment there. And when evaluating on a system cost basis, that can guide you towards a thermoplastic composite solution. And relative to metallics, the thermoplastics are they provide a much better strength to weight ratio. So the specific strength and specific stiffness are much higher, and you can see that in the blue shaded area when compared to common metallic alloys. And the other thing to keep in mind, and this will show up again later in the presentation, is that the continuously fiber reinforced thermoplastic composite forms are anisotropic in the tape format. So the properties are very directional. So you have to keep that in mind as you're designing with and utilizing these materials. But that gives you the ability to tailor and really drive a weight reduction in your parts. And I've been talking a lot about the Victrex Peak product, but what we've recently brought to market is what we call Victrex's AE250 polymer, and it is a lower melting temperature polyaryl ether ketone. So it's in the same family as Peak, but what we've done is we've slightly altered the chemistry to provide a lower kind of processing temperature without sacrificing in any material way the other properties. The UD tape format is really interesting, and the way that we produce this tape is allows us to provide this well impregnated, low void content, relatively high crystallinity tape that can be used to create parts. And when it's made from the low melt Peak product, it has a 40 degrees Celsius lower melting temperature than a traditional Peak. So that opens up some benefits, including reduced energy consumption, which is also related to lower processing temps. And we found a really robust processing window. And then the other thing that delta between the melting temperatures has opened up for us is the ability to design these what we call hybrid overmolded parts, where we use the continuous fibers in a low melt format to provide the strength and stiffness of the part and really manage the bulk of the loads. And then we are able to injection overmold with the traditional Peak, which then allows us to functionalize the part and add geometry that just wasn't previously possible. So it opens up opportunities to replace machine from metal subtractive parts with a fairly additive composite format that drives both reduction in weight and reduction in system costs when we choose the right parts. And then finally, there's a lot of information, I think, in the public domain about the use of the low melt PAIC or 8250 in UD tape format, but being processed through automated fiber placement. And we think a lot of this benefit comes from being able to move along the viscosity curve and get a better flow of the polymer while doing these rapid laydowns, and then ultimately yielding higher quality laminates from that process. And while we spent a bunch of time talking about the tape format, I just want to highlight that there is an ecosystem that's been built around this product. We have filaments, we have films, we have compounds, all that are compatible and derived from low melt PAIC polymer. And can be used with those various formats in combination with the PEEK polymer as discussed previously. So quite a good range of products to allow the adoption of the UD tape. And it's now time for our second slide, or our second poll, and would just like to review with the audience their familiarity with design allowables. And we'll give this one a good 20 seconds or so to see where everybody's background is. Okay, great. Yeah, I mean, given the SAE audience, I expected some good familiarity. So with this, I think I'll pass the presentation over to Claire, and she'll talk maybe more specifically about how the allowables are generated and used with the composite materials.
Thank you, Jonathan, for the introduction to Thermoplastic Victrex. I'm going to cover allowables data, both their generation and use. I did see from the results of the poll that a good amount of you are familiar with allowables and use them, and there are some not sure, or maybe not at all. So hopefully you'll find some information useful for you. In short, material allowables are material property values with a particular level of confidence and reliability calculated using statistical methods. Any aircraft structure substantiation requires analysis and testing at many different levels. If you see the image on the right is an example of the building block approach, where you have coupons and small articles on the bottom and moving all the way up to system level test. So the level of the building block pyramid is where all the level test takes place on pretty generic and standard using standardized testing. 1,000 plus specimens tested lower levels of the building block pyramid, and as you move up the pyramid, the tests more and more expensive and more complex. Any allowable that are associated with that are developed in the base of the pyramid are associated with the process qualification and material qualification programs that result. The material qualification programs have some amount of FAA oversight, and this ensures test and reporting quality. So what are what are the allowables used for? And primarily the information generated in the programs can be is generated at lamina and laminate levels. There are benefits and drawbacks to using lamina or laminate level information in your analysis. On the lamina side, the pros are that your material cards are easily customizable. You have ply-by-ply stresses and strains in your outputs, and that can yield more accurate results. But on the downside, inputting and your material cards or inputting the information into your analysis software can be more time-consuming and complex, and that interlaminar properties are not well captured. Additionally, the process-related effects on the outputs are lessened. On the other side, using laminate level data, it can be applied to a shell-based model, and the information is faster to implement and process in your software. And using laminate level data does capture process-induced effects. But on the downside, of course, you don't have ply-by-ply stresses or strains in your results, and there are limited inputs. Often, laminate level data is developed on quasi-isotropic or QI laminates, and additionally hard or soft laminates that have higher or lower moduli than the quasi-isotropic laminates respectively. And of course, interlaminar effects are also mostly ignored with this method. So how are allowables generated? They're generated using generally a minimum of 3 batches of material. 2 panels from each batch are fabricated, and 3 specimens typically are extracted from each panel to create a set of minimum 18 specimens for each test and condition. The conditions generally range from CTA or cryogenic temperatures dry, which is generally -65 Fahrenheit, all the way up through elevated temperature dry and elevated temperature wet testing. And typically the elevated temperature used is for testing is below the polymer glass transition temperature. This method of sampling provides data to show both material and process stability or variability. And that variability contributes towards the calculation of the allowable strength. To have a higher that program I just described is for B-basis allowables, but if you want to have A-basis allowables, which are defined as strength values where only 1 in 100 specimens will fail below a value, a minimum of 5 batches of material are used and a minimum of 55 specimens per test. For B-basis allowable programs, the strength values calculated is a value at which only 10 in 100 specimens will fail below that value. This slide shows a pretty typical test scale program for both the lamina and laminate level testing. But I'll note that this list is not exhaustive. It doesn't include everything that can be used. If your end use of the material and your program dictates something more specialized, that can absolutely be added into your program. In addition to mechanical testing, physical properties and thermal properties of the materials are also measured, such as density, resin content in both the unconsolidated and consolidated material, fiber volume and content, and expected consolidated ply thickness. Thermal properties of thermoplastic polymers that are given in these allowables programs include melting temperature, glass transition temperature, and a hot crystallization temperature. In addition to these physical properties, fluid sensitivity is also generally captured, typically using compression testing, and can include specimens that have had extended contact with jet or aviation fuels, hydraulic and engine oils, salt water, skydrol, de-icer fluid, short contact with a variety of solvents such as MEK or IPA or propylene glycol. And of course, this list is also not exhaustive if there's something more specialized that needs to be explored. So finally, where can you find information about allowables? Where can you find these databases? Major OEMs such as Boeing or Airbus will often generate their own proprietary design allowables, and those are not available for anybody but their internal engineers and possibly select suppliers. However, the National Institute of Aviation Research, or NIAR, which is located at Wichita State University in Wichita, Kansas, has the National Center for Advanced Material Performance, also known as NCAMP. NCAMP works with the FAA and industrial partners such as Victrex to generate qualified materials databases, and these are available to the public. In order to access these databases, if you visit Wichita State's NIAR and NCAMP websites, shown at the link there, and you scroll down to the bottom of the page, look for the Allowables and spec, and download the statistical analysis report as well as the material property report, you'll have what you need to input allowable strength values from those materials into your analysis. And I'll want to note that coming soon, Victrex will have their first unidirectional tape allowables database published based on the AE250 polymer Jonathan described before and Hexcel AS4 standard modulus fiber. That should be available before the end of the year. So before I hand it off to Pete, I'd like to introduce the next poll. And we would like to know, survey the audience, do you use advanced modeling techniques? I'll give you 10 to 15 seconds to go ahead and answer that poll question before I pass it off to our final speaker, Pete Levesque. Looks like we have nearly a split audience where most of you do use advanced modeling techniques. So hopefully you'll find, I know that you will find the content Pete has for you useful and interesting. And for those of you who are feeling not so sure, you'll definitely find some useful information coming ahead. Thank you. I'd like to pass it on to Pete Levesque now.
Thanks, Claire. Welcome, everybody. I'm going to talk about some advanced modeling techniques and general approaches that we use when modeling composite hybrid overmolded parts. So this first slide is a bit of an overview as to sort of why we are here and what we're doing. Typically, customers approach us or have approached Victrex in the past, and they've had a part that wants to be converted. Maybe it wants to go on a weight or cost diet. Maybe it's taking too long in a specific operation. You know, if it's a metal, maybe it's got a weight problem or a fatigue issue. Or if it's a composite, maybe it's got too much labor in it. And at the end of the day, they want to get to a mass production solution. But the path between those, sort of that identification of the application that needs some help and the mass production part, it's when converting it to a thermoplastic is a little bit daunting and is not all that well laid out. Victrex played matchmaker throughout this process in the past, where they would find designers or part and tool makers that could design a part and then partner them up with an analysis house and some of the internal expertise that Victrex has on the materials, and then potentially get it prototyped somewhere and then tested somewhere else. And all of this was a very long, drawn-out process that really was wasting years sometimes once the application has been identified. So Victrex created Victrex Composite Solutions, which is an under one roof, all-in-one solution where we're taking the whole process from start to finish, and that's what we're going to look at here. First, we get a part, and we're going to follow this part throughout our journey here, but this overhead bin bracket, it came to us, and the first thing that we do with all of our parts is identify the needs and wants of the part. And we need to quickly figure out if, even in an ideal case, one way or the other, does there exist a solution that is going to be commercially viable. So one of the big filters that we use is this buy-to-fly ratio. We look at the amount of material that is initially purchased or maybe is in that first billet that needs to go into the machine in order to create the part that flies. By the pound, our materials that are heavily using carbon are pretty light, so by the pound they're relatively heavy, or relatively expensive. but when you look at the actual buy-to-fly ratio of a given candidate application, the real cost of that $3 a pound aluminum billet might be somewhere up near $35 a pound, just based on like a 10 plus buy-to-fly ratio, which is pretty typical for what we see. That is all before it goes into the machine, and it's a pretty waste-inducing process. So once it passes that initial commercial, viability test, we then have to figure out how are we going to make this out of continuous fiber unidirectional composites and injection molded pellets. So again, a little bit of a process overview of what we do. At the beginning, there's a bit of a napkin sketch, trying to understand the problem, and at the end, it's commercial production ready part. And in the what we'll go through here is some of our digital modeling processes, methods to optimize the design, methods in process simulation that helps us de-risk some of the questions and decisions around tooling, and then prototyping, and then eventually into commercial part production. There are a few design enablers that I wanted to highlight that are made possible through this polymer. The first being hybrid overmolding. In the sort of sub-slide image there, we show what's a relatively simple composite part, just two flat plates cut into a specific shape. They themselves are stiff and hard and have all of the great properties that come with unidirectional composites. But the geometry is simple, and what we use the injection overmolded polymer to do is functionalize it, and we give those relatively simple shapes some real purpose. It also helps us, in a way, use the soft material to reinforce the hard material, which we'll get into a little bit later. And finally, it really makes for a high rate and low cost manufacturing process. Once you get into the injection molding phase, the time that is spent in the tool is measured in seconds, and that's also the case in other parts of the process. Second enabler is welding. This allows us to make some pretty complex shapes and create a welded bond across the interface. And what this is, it's not like gluing, where you might see that in a thermoset, or even like metals to metals or metals to thermosets. This is the same polymer across the interface, and it's crystallizing across the interface. So it really creates a single piece, a single part that is, otherwise in other methods would be two distinct parts with a distinct line across them. When we get a new application, the first thing we have to do is begin to understand it. What we bring to the table is process and materials expertise, but we don't know anything about the application. We need to go and ask our customer a series of questions to try to understand the part. And really, it becomes a bit of an interview of the application owner and of the part itself to try to figure out why is it the way it is. What does every detail on there do, and what about that detail can we change or omit or modify? Many of the parts that are designed for quick and easy machine manufacturing want to be a little bit different when it comes to injection molding. So what we need to do is basically tear down the existing design and get back to its original sort of fundamental problem that it's solving, and then build it back up in a new, different way using these fiber-based reinforced polymers and these different manufacturing processes and methods. I wish it were a linear path, but it's a bit more of a spiral. So what we always start with the customer requirements. Once we've gotten to the point where we think we understand what this part is doing and what's being asked of it, we then take an eye of manufacturing and try to figure out exactly, how might we build this part. And then once we're sort of through with that kind of imagination of what a potential solution might look like or how we may attack it, we have to look at it through the lens of tooling and make sure that, given the processes that we have, that it can be built. Check back in on costing, make sure that our initial assumptions on the commercial viability still apply, and then look back into the performance of the part. And this is, sort of the first pass on we've got a potential solution that ticks all the boxes. Does it do the job? But this is, like I said, not a linear process. We go back and check in on the customer requirements again, look at it again through manufacturing, tooling, costing, performance, and get a little bit closer to the final design. And we'll do that as many times as needed until we and the customer agree that this is something that can and should be built and is going to meet their requirements, and also is going to is something that has been designed for manufacturing and hits the cost targets. So, design for manufacture. One of the big problems that we face is that the materials are hot. As a thermoplastic, it's not something that can be handled and touched by humans during the process. So everything is typically done with a robot. And as smart as our robots are, they don't exactly have the craftsmanship that an operator might have. So we have to figure out ways to design the part and design the tooling to include the craftsmanship in the process. And this is either done through complex tooling, but whenever we can, we try to make the tool simple, especially in the prototype process, where you don't necessarily want to spend too much money on a tool that you may end up changing. So our poor robot here, trying to figure out how to make this paper airplane, we can make his life a little bit easier by figuring out exactly which parts of the plane need to be one material versus the other. So maybe there's a flat sheet or a gently formed sheet that is made of continuous fiber composites, and the rest is injection overmolded. And that's our job to figure out in the design for manufacturing process. We have some tools along the way that we like to use, one of which is forming analysis. And forming analysis is a way to make sure that we're not, doing anything to the materials that they won't allow for in the process. What's highlighted here is one of the effects of having a very stiff and essentially, in a relative terms, fiber that doesn't stretch compared to a matrix that flows. And in this operation, we've got to watch out for potentially squeezing matrix out of the fiber and having it pool on one side and have it be dry on the other. So we use the forming analysis to identify these sort of problematic areas, look at how it may crystallize once it hits the tool and at different times and different speeds in the process, and also how it may warp or spring back based on different cooling and crystallization rates. We use topology optimization to help us figure out exactly what the overmolded polymer should look like. So there's many times a clear or seemingly clear path for where the continuous fiber would like to be. So we'll look at a part and understand in sort of big picture terms what the load path might be, and we'll design an insert, a composite insert to take the load and the primary stresses and sort of control the overall global deflection. But then the topology optimization actually helps us quite a bit to understand how the overmolded polymer might help stiffen or reinforce the continuous fiber unidirectional. So it's a weird case of where you're using the soft to reinforce the hard, but what it's doing is it's kind of like putting a block under a leaf spring. It's helping the stiff part support itself in a way that it can't otherwise do, or is maybe too difficult to include in a insert that you're trying to keep simple. We have a lot of sort of, I guess, in our design spiral, there's a lot of other sort of sub processes that we look at to try to optimize and keep our design flow on track. One of them is in the topology process. The first thing that we do is to run a quote-unquote dumb geometry, and that's basically taking our continuous fiber insert and surrounding it with as much overmolded polymer as the design space will allow for. Fill the design space completely, 100%, so that we can run FEA on it, and if that passes FEA, if it meets the stress and really at this point deflection criteria, then we know that there's something to optimize. If that fictitious part, that you can't and wouldn't ever make, doesn't pass, then we know we have to stop and go back and look again at our continuous fiber insert. But if it does pass, then we know our continuous fiber insert is probably pretty close, and it's time to run topology and create that more optimized solution, and then run a stress analysis on that. And we'll go back and loop back and maybe modify our composite insert and run a little bit smarter version of the input to the topology optimization the next time. So this mold filling, I don't know if you can see the animation. Sometimes it goes, sometimes it doesn't. But this really is just an intro to the next slide, which I wanted to show. The point of this is that fiber alignment matters. When you're injection molding the continuous around the continuous fiber inserts, the direction of the fibers in the polymer really does start to matter. And what you're seeing in this graph is the difference between an anisotropic solution versus an isotropic solution. Throughout the part, it's not one or the other. It's not completely one or the other. It's anisotropic or sort of behaving in the anisotropic way in some areas and behaving in the isotropic way in others. But what we'll do is we'll take the results from the isotropic case, because that sort of idealized case is the best that it's ever going to perform, and we'll look then at the stresses there. But when you're using fiber mapping, you don't have to make that choice, and you don't have to sort of take that kind of best/worst case scenario. You can actually find where it's isotropic and where it's anisotropic throughout the part, given a certain loading criteria. And that really helps understand if you've got your gate in the right place, if you've got flow lines in the right orientation, and if your part really is truly optimized for that hybrid structure. Finally, the information volley. This is something that it's just another way to look at the overall design process. I think one of the earlier slides was titled concurrent engineering, and it really is that. It's a process that is collaborative throughout. and it's one that it's an ongoing dialogue and conversation. So when it's never really like a throw it over the fence and we'll check back in 4 months with prototype parts, because we do need to understand the part and understand the application, and we do need the application owner to understand the materials and the process and what can and can't be done there. So we go back and forth throughout the process, and whether it's that early sort of commercial filter and then engagement into a concept design, which will eventually transition into prototyping and manufacturing and tooling. Once we get past the prototype part and it is time to go to production, we transition the geometry and the requirements and the limitations of the process onto a drawing that is owned by the customer, so that final drawing becomes essentially the input to a build to part or build to print relationship that we have going forward. So thinking back to that very first slide, looking at the overview of the process where you have that application identified, but how do you get to mass production? This is it. This is the process by which we shepherd the design and the part through the development and then onto a final drawing where eventually it becomes a build to print relationship. So with that, I'd like to open it up to any questions.
Thank you for that great presentation, Peter, Jonathan, and Claire. And just a reminder to the audience that you can still submit questions for speakers through the Ask a Question box on screen. And now we're going to go ahead and take some questions that have already come in. First up, how strong is the bond?
Yeah, so maybe I'll take that one, Amanda, and then Pete and Claire can chime in as appropriate. So when it comes to the bond, we've done a number of studies that suggest, at least in lap shear coupons, that we can achieve a 40-ish MPa bond strength. So if you compare that to a traditional thermoset adhesive bond that's commonly used in aerospace today, which is in sort of that 18 to 20 MPa range, I think that the bond is quite good. And I guess maybe the other more qualitative answer is that we can always move the bond around, and that's maybe where I'd ask Pete to chime in.
Yeah, that's a good point. It is process related. Since we are asking the injection molded polymer to melt the surface of the underlying insert, we do need to make sure that there's temperature and time at that temperature throughout the area, throughout the critical areas. And this is done through mold flow analysis. So it's one of the tools that we use to evaluate gate position and filling parameters. But really we're trying to have the insert surface experience a time temperature sort of window that will allow for crystallization across the two materials.
Great, thanks so much, Peter and Jonathan. Next up, how big a part can you do?
Yeah, so I think we haven't seen really a technical limitation on how large a part we could do. I mean, as Pete was mentioning, like you gotta keep the polymer in a molten state and fill out the tool and manage the temperature of the interface. I think there's equipment out there in industry and in academia that's capable of making hybrid overmolded parts in the up to 5 foot by 7 foot range. In our facility in Rhode Island, we're generally overmolding parts that you could hold with, say, 2 hands. So the largest one that we've made is like 2.5 pound shot of PEEK on top of a fairly thick laminate, 1/4 inch thick laminate that is in the range of like 28 by 28 square inches. But yeah, I think there's the potential to go larger than that, but it's always just it's a function of the tool that you got to wrap around the part and the equipment to provide the appropriate temperature and pressure.
Great. Thanks so much, Jonathan. Next question. How strong is the interface bonding strength of hybrid overholding?
Yeah, so I think that's just another version of the first question. So maybe we should move on to the next one.
Sure, no problem. Is it possible to use loading bearing parts on aircraft that have been made with materials that do not have design allowables?
Claire, do you want to field that one?
Sure, I can take that one. Yes, it is possible at the expense and time taken by testing and validating the material selections is substantially more if you do not use design allowables on a part.
Yeah, and I guess just to add on to that, I think Claire showed the certification pyramid earlier, and ultimately you have to do system level testing. So if you do the system level testing and the parts perform and you can prove that they can be made repeatably, then you can fly that part. It's just a much quicker and lower cost approach to be able to design by analysis.
Great, thank you so much. Let's see. Next up, do you manage porosity due to manufacturing by design allowable or by damage tolerance approaches?
I don't know that one.
I can take that one. Since design allowables come with a process specification, defects or porosity caused by the process used will be captured in those allowables, and any variability caused by a defect like porosity will be factored into the statistical analysis used to calculate the allowable strengths.
All right, thanks so much, Claire. Next up, an easy one for you. Do you have labs or offices in the U.S.?
Yeah, we have a facility in Rhode Island that Pete kind of described, the all under one roof solution. So in Rhode Island, we have automated tape laying, a shuttle press consolidation, a automated forming press, injection overmolding, and some secondary processes, along with a lab that allows us to kind of characterize the materials that we're working with and hone in on optimizing the process, and then do some final part inspection as well.
Wonderful. Thanks so much, Jonathan. Next question. During topology optimization and understanding molding parameters, do you use percent crystallinity as a guiding metric for process and design changes?
I can take that one. Yeah, that's a good question. It's the two are not in the same piece of software that we use, so we do have to kind of do one then the other and then iterate on that. But it is something that we look at in the mold flow. So when we are sort of looping back and taking a second pass at our topology optimization, it's something that we'll factor in. But unfortunately, the two are in separate pieces of software at the moment. So it is a kind of loop back and iterative process.
Great, thanks so much. Next question. In the hybrid overmolding process, if only a portion of the fiber reinforced component is overmolded, how does one keep the non-overmolded laminate sections from deconsolidating during the high temp injection molding process?
Oh yeah, okay, good question. That's, we have parts that are, we sort of, in rough terms, refer to them as mostly hybrid or mostly composite. But you can have either one of them really with no problem. In the mostly composite parts, where say you do have like a small island of functionalizing overmold on a big sheet of composite, the actual pressure of the overmolding is so great that you don't really have a deconsolidation problem where you're overmolding. But and conversely, outside of the area where you're overmolding, the consolidation pressure of the injection mold tool is also so great that you still don't have that problem. And the injection mold tool, is below melt of the low melt opaque continuous fiber, so you don't really reach a temperature where that would be an issue. So it's not a big problem that we have to worry about. So good question though.
Okay, great. Thanks so much, Pete. Very informative. Next question. Can these parts be used as temporary parts until manufactured parts are made for aerospace?
Could you repeat that one? Oh,
absolutely.
Okay. Yeah.
Can these parts be used as temporary parts until manufactured parts are made?
Well,
I think,
go ahead, Jonathan.
Yeah, I think the goal is that these parts require, specific tooling and an approach to manufacturing. I think if the idea is that you fly these parts, when prototyping, we will do things like injection mold, some of the functional pieces and either weld them or adhere them to the composite so that we can, or 3D print them so that we can get some faster prototyping and lower cost of iterating. But I don't really see a world where you would use these hybrid overmolds as a temporary solution to something, just given the non-recurring costs associated with them.
Okay, thank you so much, Jonathan. Next question, who should one contact at Victrex to explore a potential collaboration for product development?
Yeah, you could reach out to me directly, jonathan.thirks@victrex.com. And we'd be happy to take a look at your project or your application.
Thank you so much, Jonathan. Let's see. Next question. How do you do hybrid overmolding of different polymers?
Yeah, so it's possible and it's been done. It's in some ways it's a more complicated path to certification. And then things like one of the other audience members where they asked about unconsolidating or delamination during overmolding, that becomes a more significant risk. So, building a robust process to create an overmold while you're using, other polymers or completely dissimilar polymers, while it's sort of, I think, technically possible, it's a lot less convenient and a more challenging cert path.
Thank you. Good to know, Jonathan. Next up, what are the cooling rates post-processing?
I can take that one. They're typically the process is designed to maximize the crystallinity window. So it depends on the part, sort of how much thermal mass it's got, but we will at the part level change the process parameters to maximize crystallinity.
Great, thanks so much, Pete. Are you able to apply strength on fibers during injection?
If this is maybe asking about like stress on the fibers during injection, I guess I'll answer it that way. During the injection process, it is possible to, if you're not careful, if you haven't sort of designed around it, it is possible to sort of move the fibers because you do potentially melt the matrix around them or the matrix supporting them. So you want to design a part such that you're melting the surface, but maybe not melting the core of the insert. So there have been parts where we are looking at the stress on the fibers or the stress on the laminate during injection molding, but typically it's something that we sort of try to design around.
Yeah, and I know we're running out of time here, but just maybe also what some of these lines of questions are getting at is maybe like one-step versus two-step overmolding, and we look at that regularly in the design phase. Does it make more sense to form the composite part and injection mold in a single step, or to form in a discrete step and then injection overmold afterwards? And generally, we find that the two-step makes more sense.
Great. Thanks so much, Jonathan. Well, with that question, we are at the end of our webinar. I would like to thank Claire Stagel-Murphy, Jonathan Sirks, and Peter Levesque, as well as our audience for joining us today. And thank you to everyone who sent in questions. We'll supply the speakers with any we didn't get to so that they can follow up. As a reminder, you may download a PDF of today's slides under the Event Resources tab on your screen. In just a moment, a survey will pop up. Please tell us what you thought of our program by answering these 3 questions. This webinar will be available on demand, and an email will be sent to everyone who registered as soon as the archive is ready. Once again, thanks for watching.